trigonometric substitution. This is a lot like U substitution, except you're going to use trig functions. You won't use just U equals x squared. You'll use trig functions. All right. The idea behind this, this is used in situations where you have both x squared and a square root. And it's going to be used in order to eliminate the square root. The square root thing is usually the thing that's causing us problems. We're going to use it to get rid of that square root. Here's the whole idea behind it. Everybody usually remembers this formula. Sine squared x plus cosine squared x equals 1. Except I'm going to rewrite this formula. I'm going to rewrite it as cosine squared x equals 1 minus sine squared x. So if you're looking at your integral and you see something that has a square root and it has a squared minus x squared, you're going to use the trig substitution x equals a sine theta. Why? How is that going to help? How is it going to help to not write x squared, but rather replace x with a sine theta?
Because we're
You have the equivalent cosine.
That's exactly right. This will become square root of a squared minus a squared sine theta. And how can you simplify that square root?
remove it.
You can factor an a squared out. So that becomes square root of a squared times 1 minus sine squared theta. And here's the whole reason for doing this. What's 1 minus sine squared? Cosine squared. That becomes square root of a squared cosine squared theta, which is a cosine theta. So that's why we use trig substitutions. We use trig substitutions to get rid of square roots. That's the whole idea behind this. So if you have square root of a squared minus x squared, your substitution will always be x equals a sine theta. Now, there are other forms of this Pythagorean identity. For example, if I take this Pythagorean identity and I divide everything by cosine squared, I get another form. What's sine squared divided by cosine squared? Which one squared? Tangent squared. That's tangent squared x. Plus, this is the easy one. What's cosine squared divided by cosine squared? 1. Equals secant squared x. So, if you see a square root of x squared plus a squared, you'll make a different trig substitution. Your trig substitution will be x equals a tangent theta. Why would I use a tangent theta?
Then you can factor out an a squared and have tangent squared plus 1.
When I plug that in, I can factor out the a squared, then I'm going to have a tangent squared plus 1, which changes to a secant squared, and everything reduces. So when you make this substitution, this will all reduce to be a secant theta. Once again, you'll get rid of that square root. That's the whole idea behind this, is get rid of the square roots. So, the third possibility. There are basically three possibilities. We could have a squared minus x squared. We could have x squared plus a squared, which of course is the same as a squared plus x squared. I could switch the order. So a squared minus x squared plus a squared. What's the third possibility? X squared minus a squared. If you have x squared minus a squared, you're going to let x equal a secant theta. Why in the world would I use a secant theta?
Tan squared theta, or tan squared x would be secant squared theta x minus 1.
If I move the minus 1 over, that's exactly right. I get secant squared minus 1. So when I plug in, I'm going to end up with a secant squared minus 1. That will become tangent squared. So when you do your substitution, this will become a tangent theta. We get rid of all of the square roots. All right, so basically what you need to know in this section is your three substitutions. There's substitution number 1. If you have square root of a squared minus x squared, x is a sine theta. Substitution number 2. If you have square root of x squared plus a squared, x is a tangent theta. And finally, possibility number 3. If you have square root of x squared minus a squared, x is a secant theta. Those are your only 3 possibilities. Questions on that? All right, so let's look at some problems. Oh, by the way, I'll talk about that in a minute. We'll deal with that here when we get back. How about integral of 4 divided by x squared square root of 16 minus x squared dx.
Change out the square root and everything in it for sine.
Well, what should our substitution be? X is, and a is the number 4. So our substitution is going to be x equals 4 sine theta. What's going to happen with the square root? Square root of 16 minus x squared will become square root of 16 minus 16 sine squared theta. So that's going to be square root of 16 times 1 minus sine squared theta. But 1 minus sine squared is cosine squared. So when I take the square root of that whole thing, I'm going to be left with 4 cosine theta. So there's my 2 substitutions so far. X is going to be 4 sine theta. So down here for this x squared, I'm going to plug in a 4 sine theta. This square root thing is going to be 4 cosine theta. But I also have to substitute for the dx. If x is 4 sine theta, what's dx going to be? Well, what's the derivative of 4 sine theta? 4 cosine theta d theta. So there's really 3 substitutions I need to make. For this x squared, I'm going to plug in 4 sine theta for x. For the square root thing, I'm going to plug in 4 cosine theta. And finally, for the dx, I'm actually going to plug in 4 cosine theta d theta. So it's very similar to u substitution, where you're letting, typically we let u be something before, now we're letting x be something, but we still need to take our derivative and make that substitution also. All right, so we get this whole integral becomes, I have the 4 right there. For x squared, that becomes 16 sine squared theta. the whole square root thing, that's a 4 cosine theta. And then the dx is 4 cosine theta d theta. All right, so there's trig substitution. Now, after you do trig substitution, notice what you end up with. You end up with an integral that has a bunch of sines and cosines with powers on them, which is what we did in the last section. So you do trig substitution, and that reduces it to be a problem that we did back in section 8.3. So now we have to remember everything we did in section 8.3 and do those problems too. So this is like a double bonus section. You get new material, you get the trig sub, and then you get a review of the old material. All right, how are we going to integrate that? I can cross out the 4 cosine thetas, and then 4 and 16, that reduces to be a 1 over 4. Integral 1 over sine squared theta d theta. All right, so how do you integrate 1 over sine squared theta? There's a formula we have. Excellent. What's the formula? It's on the note card. How about, this is the same as 1/4 integral of cosecant squared theta. And that's one that you were supposed to memorize back in Calc 1. What's the integral of cosecant squared?
Cotangent. Negative cotangent.
Negative cotangent, because the derivative of cotangent is negative cosecant squared. So the integral of cosecant squared is negative cotangent. So that's negative 1/4 cotangent theta plus c. Now, we're not quite done. Oh, why not? What the heck is wrong? Our integral started with x. Our answer should end with x, not end with theta. All right, so here's what we're going to do. We're going to come back to this. And I'm going to write this as sine of theta equals x over 4. That's true. Theta equals arc sine of x over 4. But then I don't really want to have a cotangent of arc sine. That's pretty ugly. We can do better than that. What we're going to do is we're going to use this little fact to draw ourselves a triangle. It's supposed to be a right triangle. Mine doesn't look like a right triangle, but it really is. This is our angle theta. So opposite over hypotenuse, because I know sine. Sine of theta is x over 4. I go talk to my good buddy Pythagoras. How long's the other side? Square root of 16 minus x squared. Final answer, therefore, is negative 1/4. How do I find cotangent? Adjacent over opposite. So the answer is square root of 16 minus x squared all over x plus c. Questions on that one? So it's a lot of back and forth. I agree. You do a trig substitution, which forces you to have a problem that's powers of trig, which sends you back to section 8.3. You do the integral technique that you learned in section 8.3, but then you got to jump back, go back to your trig substitution and do a resubstitution in a sense to get your x's back. I agree. A lot of back and forth. Generally not the easiest problems in the world.
Are there shortcuts?
Not that I'm aware of. The one thing I would point out with this problem, we could have, if we wanted to, use x equals 4 cosine theta? How would this square root thing change if I had 1 minus cosine squared there? 1 minus cosine squared would be sine squared, so I'd end up with 4 sine theta. But you never see anybody do that. You never see anybody use x equals 4 cosine theta. Why not? Because when you take the derivative right there, you're going to get a negative 4 sine theta, and you're introducing another minus sign into the problem, which is easy to lose along the way and screw up. So you could use x equals 4 cosine theta if you choose to. You're going to introduce a minus sign right there, and it's one more thing to have to keep track of. So you never see it done that way. It's always x equals 4 sine theta. Always, always, always. If you want to be daring and use minus signs, you can. How about the integral? Square root of x squared plus 4 divided by x to the 4th dx. All right, so we got to flip back, and we got to look on our chart. What do you do when you have square root of x squared plus 4? What was our substitution?
X equals 8 tan theta.
So x is going to be 2 tan theta. Then we got to do this little work here. So the square root of x squared plus 4 becomes the square root of 4 tangent squared theta plus 4. Factor the 4 out. That's square root of 4 tangent squared theta plus 1. We use our Pythagorean identity. Tangent squared theta plus 1 is secant squared. So when I do square root, I'm just going to be left with secant. So this is going to be 2 secant theta. Again, the whole idea behind these is to get rid of the square root. That gets rid of the square root. Last thing we need to do is come up here, take a derivative. What's the derivative of tangent theta? 2 secant squared theta d theta. Make all the substitutions. We have the integral. The square root thing became 2 secant theta. Then I have x to the 4th on bottom. That's going to be 2 to the 4th. 2 to the 4th is 16 tangent to the 4th theta. And then my dx finally was 2 secant squared theta d theta. All right, so simplifying a little bit, up on top, 2 times 2 is 4. 4 divided by 16, that's a 1/4. Integral secant cubed theta over tangent to the 4th theta d theta. All right, how do you integrate that? Okay, secant has an odd power. Unfortunately, as I recall, we want secant to have an even power. Because what I'd really like to do, I'd like to do a u sub. I'd like to let u be tangent. But the derivative of tangent is secant squared. So you want secant to have an even power, or you want tangent to have a odd power. What do you do if you have the opposite? Oh crap, you say. What do I do? If you have the opposite, you switch everything to sines and cosines and hope it works. Alright, so 1/4 integral. Secant cubed, that's going to be cosine cubed x divided by sine cubed x.
It's still theta, correct?
Oh, theta, I'm sorry, yes, theta. Thank you. Divided by 1 over cosine to the 4th theta. Oh, heck, I got that all upside down, don't I? Oh, good. You couldn't see anyway? Good. I didn't have it all wrong then. Ignore that part that's all scratched out. That wasn't wrong. Try again. 1/4. Integral. Secant cubed, that's the 1 over cosine cubed. Theta. And then the tangent to the 4th down on bottom, that's going to be sine to the 4th theta over cosine to the 4th theta d theta. Flip and multiply.
Cosine over sine to the fourth.
When you flip and multiply, you get cosine over sine to the 4th. So that's 1/4 integral cosine theta over sine to the 4th theta d theta. The big question now is, did that help? Yes, because u is sine, and the derivative of sine gives you that cosine. All right, so now this becomes a u substitution. U equals sine theta. du is cosine theta d theta. 1/4 integral 1 over u to the 4th du. What's the integral of 1 over u to the 4th? No natural log.
1 over u to the third.
Right, you got to think of this as u to the negative 4th. So you can add 1 to your power. That's going to give you a u to the negative 3. And divide by negative 3. So that gives us negative 1/12 u to the negative 3 plus c. We're getting close. That's negative 1/12. U was sine theta, so that's sine to the negative 3 theta plus c. Finally, we can finish this one when we plug our x's back in. So we got to go back up here to this and use this to draw a triangle. Tangent of theta is x over 2. Triangle. Theta, so it's x over 2 like that. Opposite over adjacent. Pythagoras says the hypotenuse is?
Square root of 4 plus x squared.
I'm going to write it as square root of x squared plus 4, but square root of 4 plus x squared would be the same. So finally, final answer. Negative 1/12. And then sine is opposite over hypotenuse. So that's going to be x over the square root of x squared plus 4. And that entire thing gets raised to the negative 3 plus c.
So the homework's going to be like 2 problems, right?
The homework's going to be lengthy, isn't it? Yes. Long problems. Absolutely. Lot to mess up. Lots of steps, lots of places to make a simple mistake, which blows up the whole problem. I agree. Now, I do want you to notice something. Notice that this problem up here started with a square root of 16 minus x squared. And when we drew our triangle, what was the missing side? Square root of 16 minus x squared. This problem started with a square root of x squared plus 4. And when we drew our triangle, what was the missing side? Square root of x squared plus 4. That should always happen. So whatever square root you're trying to get rid of should come back to haunt you when you draw your triangle.
So I mean, you don't have to draw a triangle if you know.
I still think it's a good idea to draw the triangle so that you make sure that you're getting the opposite and the adjacent and the hypotenuse all in the correct spots. But the missing side should always be the same as the problem that you started with. So I think it's good to draw the triangle, but I don't think you actually have to go through and work out the Pythagorean theorem and get the third side. It should always drop right out to be that square root that you started with.
So if you get there and you don't get that, you know you already did something wrong.
If you get there and you don't get that, you know you messed up somewhere, yeah, and then you gotta go back and try to figure it out. Not easy. Other questions?